Студент не выше. Ну да, скорее всего, сейчас меня.
All right, good morning, everyone. Thanks for joining this lecture. Yeah, we are about to start. Let me join the Zoom chat from the other screen, and then we could follow up all the questions and stories that we do have to discuss. Yeah, here is it. All right, good. So now we need to share the screen. All right, so let's do that. Meanwhile, we almost reached the end of the first module. I'm happy to celebrate that with you guys. It was a pretty long stuff, and a pretty complicated stories were discussed. We are going to be, well, basically, I'd like to discuss some of the minor problems from multiple choice section, pre-response section of the midterm exams. I mean, the past papers. All of the files, I mean, the PDFs with the past papers are going to be shared with you today on the Telegram channel. And you'll get some sample mocks and sample exams to practice with before the URL and examination starts next Saturday. All of the instructions, sorry, all of the instructions are going to be shared within the next week. So you are going to be informed where you are located. I mean, which room you're assigned to write the exam. We do suppose that online examination is strictly prohibited. So only offline mode is available. And for you to recap, we scheduled to start on the October 23rd. You are expected to be there by 9:45, and then you'll get some 15 to up to 20 minutes to have a seat. You're going to be allocated to various rooms, and you should be aware about where you are located. The location lists are going to be shared within the next week. The exam starts at 10 a.m. So this is start, and terminates within 2 hours. So that's the end of the exam. Hopefully I'll see you there, and you see me there as well. Well, you do know your class teachers, but yeah, that's fun that you never saw your lecturer. That's really fun. Some of you could think that I'm in artificial intelligence generated voice, but here's I'm kidding. All right, so you are allowed to pick a calculator. It must be non-scientific one, so a very basic one, and that's all what you need. Well, plus some pen and pencils. You are going to be provided with the scratch of paper to write your solutions. You are going to be provided with the normal distribution table. And this is the only you'll need. to highlight, no one is going to be allowed to leave the room before the exam is terminated, or he or she submits his or her solution without any option to come back and carry on what he or she stopped. Well, that's a kind of very basic overview about the rules of the examination. And as I said a week ago and about 2 weeks ago, you are going to be provided. So basically, the exam is going to possess 2 sections. The first section is a multiple choice section. And you are going to have there about 10 questions. And the 3 response section. In the 3 response section is going to have about 4 questions. So yeah, I used to collect the multiple choice section after half an hour. So basically highlighted that about 3 minutes is allocated to solve each of the problems, but I'm not going to do that this year. You may decide your own how you wanted to allocate the time given to you to solve the problem, so you are free to do that. All right, so this was about the examination. Now about topic list. Well, the topic list. We had defined what discrete random variable is. We defined some properties of the probability. Then we had played with a full probability formula, plus we had implemented the bias probability formula as well. What else? We had defined what what conditional probability stands for. The conditional probability definition. And by the way, here we defined what the marginal probability is and what joint probability is as well. So that was defined. Then we presented some distributions. And the distributions were the following. So we implemented the geometric distribution. Then we presented some Bernoulli's distribution and the binomial distribution as well. And by the end of that, we had presented the matrix that allows us to compare some of the probability distributions. So these were expectation, variance, covariance, and correlation as well. And then you got to know all of the formulas that you need in order to be able to evaluate all of them. After that, we said, look, this is not the end of the story. And here might be some continuous distribution. So your variable might be continuous. And we presented 2 possible continuous probability distribution, probability density functions. So this was a uniform distribution and the normal distribution as well. And actually, this was a full curriculum. Well, this a full curriculum of topics we covered this module. That was pretty good, pretty nice job. Next module, we are going to dip in the continuous probability density functions, and we will then go into some details, what the continuous PDF stands for, how it looks like, what sort of properties it gives to us, and how it could be applied in order to play with the real data sets. But this is going to be the second part of the story. And actually, each of these topics that I just wrote here, plus all what was covered at the lectures and classes as well, is going to be included into the examination problems. So you have to be full clear with no doubt that you are good with these problems. Well, if you have some questions, troubles, challenges, that's probably the best time now to ask all that in order to highlight, if any, of was stays to be a problem. Just to make a quick follow-up by what we have presented last week, so we said that two genius mathematicians, I mean De Moivre and Gauss, they both presented the framework to analyze the random variable such that we think that the most likely observation is going to be those observations that equals to the expectation. And that distribution was called to be normal one. And then we said that the reason why this distribution became so popular is that these two guys, they have succeeded to calculate the probabilities of each of the cumulative density function related to the standard normal distribution. And by saying standard normal distribution, I do mean those distribution that has a zero expectation and the variance equal to 1. To recap, if I said that if y had a normal distribution with an expectation mu and the variance sigma squared, then a PDF of y would be 1 divided by square root of 2 pi sigma squared times the expectation minus a fraction divided by 2 sigma squared y minus mu squared. So this tends to be a probability density function, of a normal distributed random variable. While if x was a standard normally distributed, then a PDF of x is 1 divided by square root of 2 pi times an exponent to the power minus x squared divided by 2. And here is a standard normal distribution, while that one, I mean the right-hand side, is a normal distribution. Well, basically it is normal distribution. And besides that, we said the cumulative density function is very often to be applied. And the CDF, cumulative distribution function, tends to be an F capital of x given some threshold. So it's a probability that x is lower or equal to x small, or we define that as an integral from minus infinity up to x small, f of x d dt. So basically it's an integral. And if you recall what was said a week ago, I mean, look, now we have a continuous random variable, and the amount of the outcomes goes to infinity. Well, obviously then the probability of being at point tends to be 0 because only one possible outcome does satisfy us, while the rest, while the total number of outcomes goes to infinity, and actually that makes the probability at point going to 0. As a result, we say that the marginal probability framework is never applicable here. And this is the reason why the CDF framework is applied. And CDF stands for a probability of being less or equal to some threshold. And those values of a CDF are actually calculated at these blue colored table. So this stands for a probability of being less or equal to some threshold associated with the standard normally distributed random variable. And if I say pick minus 1.8 here, and let me grab 0.08 there. So if I want to know the CDF of X, given that X has a standard normal distribution at minus 8.88, so basically it is a probability that X is less or equal to minus 1.88. This probability is going to be 0.0301. So I just captured it. And this is the way how the normal distribution table works actually. What's the nice is actually is the following statement. The reason, well, it's not the only it's not the only reason why a normal distribution is so popular, but it's an extra explanation of its popularity. So what Gauss proved is that if you calculate the average of a random variable that you analyze, so it doesn't matter what random variable you has, if you measure the average of these random variable, then it appears that no matter what distribution this random variable has, the average is going to be normally distributed at the limit. So basically it stands for the following. The more observation is picked in order to calculate the average, the closer the the closer the distribution of these average is going to be towards the normal distribution. So basically it means that the greater sample you has, the closer all of the distributions that ever exist in the world are to the normal distribution. And actually that's pretty shocking. That's pretty shocking because it means that once you replaced a unique observation by the average, the more data you use in order to calculate the average, the closer the distribution of this average is up to the normal one. So then you may replace it no matter what sort of the complicated distributions you have. Or if you fail, say for some reasons, if you fail to identify the probability distribution function associated with random variable given to you, then you may say, look, for some reasons, I'm going to replace X by X bar, I mean by the average. And if goes to infinity, the distribution of this X bar is going to be normal one. And this helps very often. It helps to analyze the problems. But again, it's kind of pretty nice theorem because it gives us those opportunity to replace one distribution by another. But the cost of that, I mean, well, you know, all of the benefits, they do have some price, and this benefit has its price as well. And the price is that we never know the minimum number of n that is fine to guarantee this convergence? Well, hopefully you trained your calculus skills on the first year of studies, and you know that although Cauchy proposed the limit definition, it still takes some observation before we say that all of the values are close to the limit point, and that and that may happen after various elements. And actually, the similar problem is here. Although we do know that, probably these convergence exist, we never know when and where we could stop and claim that one of the distribution is replaced by another. But this is going to be discussed in details next module. Now, I would propose to do some of the problem sets and problem pools picked from previous year exams. So here I captured some of the bright problems from the past papers. I mean, the previous year midterm exam and the midterm that was conducted 2 years ago. All right, so here's a problem. This problem was actually the multiple choice section, as you guess, because the answers are proposed here. You have two random variables, and you are proposed with their joint distribution. The probability allocation is actually given at the table, and the values x and y equals to are known as well. Could you please evaluate the covariance of this metric? So I would propose to do the following. Let me give you a minute, and then after a minute, I will start trying to solve this problem. But here you need to recall what covariance stands for, and you need to evaluate its value. All right, the time started. I will start in a minute. So do your best not to evaluate it. All right, so basically, what we know, well, we know that the definition of a covariance is actually an expectation of the multiplication of two variables subtracted with an expectation of x times an expectation of y. And the expectation of multiplication of x and y is actually what? So it's well, it's a sum across the joint distribution table of all of these possible outcomes multiplied by values. So I have what? I have 0 x equal to and y 0 multiplied by 15% plus 0 x 1 y multiplied by 0 1 plus 0 x y equal to 2 times 0.15 plus 1 times 0 plus times 1 times 1 plus 1 times 2. All right, so this is 0, obviously, that's 0, 0, 0. All right, so I have 0.4 plus 0.2, so 0.6. Then I need to evaluate the expectation of x and the expectation of y as well. In order to do that, I need to know the marginal distribution. And here, what I'll do, I say that x is equal to 0 with probability 0.4, and x is equal to 1 with probability 0.6. Then I have 0.04 plus 1 times 0.6. And the probability of y, the probability distribution of y is 0.25, 0.5, and 0.25 here. Then the expectation of y is 0 times 25% plus 1 times 0.5 plus 2 times 0.25. And it's gonna be equal to 1. Well, then we say the expectation of multiplication is 0.6 minus 0.6 times 1, so it is 0. And here we got that covariance is 0. Well, if the covariance is 0, I am allowed to say that two variables are not correlated. They are not correlated. Then x, y, uncorrelated. But if I am asked whether they are dependent or independent, well, I have no idea about their independency. Well, this is because the independence is a property of the probability distribution and those properties. But there are two different probability distributions, those that is assigned to the population and those that I had evaluated. So here what we did, we grabbed some distribution that was given to us. It probably was based on the observation, and the covariance is a sample metric. So it's basically, well, it is based with the data given to us. However, if someone told me that x and y are independent, then I would know that x and y never happen simultaneously. Then I would know for sure that it is impossible to get such a covariance that will be non-zero. All right? So it's not two-way street, it's a one-way street. If x and y are independent, then their covariance is 0. If they are covariance is 0, then they are uncorrelated. But unfortunately, we do not know anything about independence. All right, then let's do this problem. Very nice one. Could you please try to do that? Let me give you half a minute for you to try. Well, if you have calculated the result, do not hesitate to text that at the Zoom chat. Let's make some votes about what you expect to be correct. So you guess it is E. All right. Let's try to do that. So, well, I know that U and W, sorry, are defined with those applications. All right, so the correlation of U and V stands for a correlation of 2x plus 1 and minus y minus 2. By the definition of the correlation, we know it's going to be a sum of all possible pairs plus covariance of 2x minus 2 plus the covariance of 1 y, the covariance of 1 and minus 2. This is 0 because it is impossible to be correlated if one of the elements is constant. So basically it does not fluctuate, and since it's not fluctuating, their covariance tends to be 0. This is 0, this is 0 as well. And then we have -2 times covariance of x and y. And the covariance of x and y, sorry, I'm very sorry. The correlation of x and y was 0.2. So it's supposed to be -0.4. And I guess that it is a B result, hopefully.
And can you explain again how you like get from correlation to covariance in the
That's my bad. No, that's my typo. This was my typo. I'm very sorry. This must be correlation as well. So we said that a covariance of A plus B, C plus D term has the following property. So it's covariance AC plus a covariance AD plus a covariance BC plus a covariance of BD. So this was a property of covariance, and similar property could be applied to the covariance as well. Oh, sorry, to the correlation as well. Any questions so far?
I think you do have a typo, because like the second term should be covariance of A and D, not A and B.
Yeah, you're right. I'm very sorry about these typos today. So hopefully I'll do all of the possible typos today so that no typo happens on the exam. Any questions so far?
Yes, why did we cancel the second summon on the, like?
Could you say it again, please?
Okay, when we were calculating the correlation,
Right.
why did we cancel the second summon?
That term you mean?
Yes, yeah.
Well, that's a very good question. Look here, one of the term is a constant because it's -2, all right? And what correlation says, well, the correlation is actually a normalized covariance, all right? So you have a covariance that measures the an amount of common fluctuations. And if one of the variables tends to be fixed, then common covariance tends to be 0. As a result, the correlation is 0 as well. Because look, the definition of the covariance was a sum of the probabilities multiplied by x minus expectation of x and y minus the expectation of y. And if one of the elements is constant, then obviously the expectation equals to itself, and then one of the brackets is 0 and the total value is 0.
Okay, makes sense. Thank you.
Well, at least
Sorry.
you had, yeah, please.
Sorry, continue, then I will ask a question.
Well, I was proposing to move to the next problem.
Excuse me, in correlation, we also need to change correlation of A and D, not A and B.
Touché. Fair enough.
So my question was, don't we have a constant in the first term with 2x and -4?
Well, it's not a -4. I'm very sorry about the way how I do, right?
It's
It's
y, right?
-y. Yeah, that's my bad. I'm very sorry.
Thank you.
Well, I have a question about another topic. Could you please repeat what Bernoulli distribution is and where to use it?
All right, we will touch all of these problems. So it's gonna be in the next couple of problems. All right, so at least we had practiced that. Now let's move to the, is it No, we will come back to that. So you asked about the Bernoulli distribution. And although I had a lot of them, oh yeah. All right, so we will discuss the Bernoulli distribution because, well, obviously I have had some problems related to that. But now let's do a problem that is very, very close to that. Let's do this one. Right, so this problem was at the exam 2 years ago. Let me give you half a minute for you to try to solve it, and then we will solve it jointly. So here we do basically analyze the problems that are given to us. Any guess what the result here is?
.94.
So you think it's 0.94. All right, let's try. So we have two independent trials, right? So as we said that both of them are independent, then we know that their covariance is 0. Each of the trial is either successful or unsuccessful. And the definition whether it is successful or unsuccessful, this framework is actually those that is defined by Bernoulli distribution. Well, Bernoulli distribution claims that each of the trial is either a success or a fail. And going back to the question that was raised, X stands to be a number of trials till the first success is observed. So if this was X, then X would be geometrically distributed, all right? But what Bernoulli distribution says is that if you had one trial and the probability of success is pi, then probability of fail is 1 minus pi, and well, that's it. But if you recall the binomial distribution appears to be a combination of Bernoulli's distribution. So speaking of Bernoulli distribution, it's a kind of simplified case of the binomial one, given that you had only one trial, only one attempt. So this was kind of highlight on the previous question. And now let's do this problem. So I know that probability of success at the first is 0.8 and second is 0.27. And I want to know the probability that at least one success is, well, it's 1 minus the probability that 0 successes are observed. Well, because of the complementary events, you are totally right to say that it should be 1 minus 0.2 times 0.3. So it's 1 minus 0.06. Obviously, that's very good. Now let's discuss here some of the binomial properties. So say X has a binomial distribution with 7 trials. So the total number of trials is 7. And the probability of success is 0.8. So this is a binomial framework. The question is the following. what is the probability that exactly two success is observed out of the list of 7? So let's evaluate the probability that x is equal to 2. Any guess what the result stands for?
Well, it's 7 choose 2.
Well, if you compute that, if you calculate that,
Why do we need to calculate it? It's
because
less than
this is
1. It's only thing that we need.
so you think that it is less than what?
Less than 1.
Come on, all of the probabilities are less than 1. Actually, on the exam, you are supposed to calculate all of that because you are going to be allowed to use your calculator.
It's 0.004.
Right, so basically it's going to be a number of the combinations by 2 out of 7 times 0.8 to the power 2 times 0.2 to the power 5, all right? So then you have 7 factorial divided by 2 factorial by 5 factorial times 0.64 times 0.00032. Here, if you simplify, you get 7/6. That gives you 3. Well, the final value is going to be 21, 64, and 0.032. So this is your probability there. Well, the only disadvantage of the binomial distribution is that it provides a formula of a probability distribution function and provides no formula for the CDF. And if you were set to evaluate the probability that x is less or equal to 2, for example, you would need to estimate the probability at 0, the probability at 1, and the probability at 2 as well. So it is multiplied here. But it seems to be very, very tiny. Yeah, you're totally right. All right, now let's do these problem. Any questions?
Yes, I got a question. The binomial distribution here, if I understand this correctly, should be ensuring that we have 2 successes, exactly 2 successes in this in these 5 trials we attempt. And here in the description of the task, we want at least 1 success out of 2 trials. Did I misunderstand something, perhaps?
Well, it's not a misunderstanding, but here was the first problem, and then we decided to do another problem to do some extra practice. So these 2 areas, they are not associated somehow. So I just proposed another problem. So you may call this as a problem number 6.
I see. Sorry.
No problem. You're welcome. All right, let's go to the next one. Here is a problem, and you are given with 2 random variables. you do know the the expectation and the variance of x and y, and you know the variance of their difference. So here's a question: could you please evaluate the correlation of x and y? All right, so let me give you half a minute to evaluate the correlation of x and y. Well, obviously, if you grab the formula of the variance of difference, it is equal to 4 variances of x plus a variance of y minus 2 covariance of x and y. And this is 4 times 9 plus 4 minus 2 covariances. Then you may say that the covariance, it is actually what? So a covariance of x and y is 40 minus 25, so it's 15 divided by 2. Then a correlation of x and y is 7.5, so it's a covariance divided by the sigma x and sigma y. So it's 7.5 divided by 3 and divided by 4. So it's 7.5 divided by 6. So here we had a variance of, we got minus 2 covariance, so it's 4 times 9, so it gives you first 6. Here is 4, so the total quantity is 40. Then you subtract 25, and it gives you 15. Once we divided that by 2, well, what is said to be said now, well, that's pretty big, but this problem does has a typo because, look, the correlation is not allowed to be greater than 1. And the problem here is that a difference of these covariance cannot be that. So we did all of the calculations correctly and all of the formulas were properly applied, but the covariance, the correlation is bigger than 1 here. That is actually impossible because we said that correlation is always from -1 up to +1. Well, if that happens on the exam, then you claim that there is no correct result at the problem. And if you write at the table where you are supposed to write the correct values, the correct answers, if you write the proper value, then the problem is going to be excluded out of list to be checked, but you'll get an extra bonus for identifying these typo. All right. Any questions so far?
No questions.
Then I would propose to do this problem that is actually related to the normal distribution that we discussed a week ago. So here you have X with normal distribution. It has an expectation equal to -2 and the variance equal to 0.1 squared. Now let's evaluate the probability that X is allocated within this interval. So let me give you half a minute for you to try to evaluate it, and then I will help you to estimate this probability. Any guess what it equals to?
Probably we have a formula for that with 5 functions.
All right, so let's try to do that.
It will be the phi function of minus 1.735 minus expected value.
Well, in order to do that, what we are going to do, we are going to subtract the expectation first. So it's going to give you minus 0.18 less than x plus 2 minus, so it's going to be 0.265. And then what we do, we need to divide by the sigma here. That is actually 0.1. And actually, what we do know, we know that x minus mu divided by sigma could be actually replaced by the standard normally distributed random variable by z. That is actually, that could be checked at the standard normal distribution table. And here you get so here you get a random z that must be greater than minus 1.85 and must be less than 2.65. All right. So then you go to the standard normal distribution table and you say that we need to find a cumulative distribution function of z being less than 2.65, and we need to subtract the cumulative distribution function of z being less than minus 1.58. And actually, that's the whole problem. So now if I go back to the to that table, so let me grab minus 1.5 and 8, so it's 0.057. So this is 571, and the probability of z being less than 2.65 is actually the same probability as z is bigger than minus 2.65, or it is 1, then as 1 minus the probability that z is less than minus 2.65. And actually these could be found as well. So here is minus 2.6. Here is a column of 5, so it's 0.004. So it's 0, 0, 0, 4. So it gives you 0, 9, 9, 6. And then a total quantity of that is, so it is equal to 0, 9, 9, 6 minus 0, 0, 5, 7, 1. And that gives you a total probability.
Sorry, how did we make a step between P of Z and 1 minus P of Z?
So we know that a normal distribution is a symmetric one. What this table gives you is the probability of being less than some value. So I had minus 2.65 there. Apparently, because of the symmetry, it is the same probability as Z was greater than 2.65. But since this area gives you total 1, so a full sum of all outcomes, I mean, the total sum of probabilities across all the outcomes is 1, you know that this event and that event, they are complementary. So I said that probability of being less than 2.65 is 1 minus the probability of Z being greater than 2.65. And that was my flip in order to make this double simplification.
Sorry, but can you explain this line above about, I don't really understand the step when, for example, in the left side, we see that minus 1.58 is less than Z. And then in the right, we count that Z is less than minus 1.58.
All right, so if I grabbed the correct value, what you were looking for is actually this area, all right? So let's have a look on that. We are asked to evaluate the probability of Z being located from that point up to that point. So we are asked to estimate the probability that we are located inside this interval. Because of CDF applied here, I say that we need to know the probability of being less than B, so it stands to be that part, minus the probability of being less than A, that stands for this part. And actually this was a split of that probability into a difference of two probabilities.
Oh, okay, I get it. Thank you.
Shouldn't be 1 minus probability of that less or equal, because on the left side we have.
Could you explain again, please? Are you about that part?
No, in the bottom we have probability of that greater than minus 2. Yeah, and the next step should be 1 minus probability that less or equal.
Oh, that's a very smart question. That's a really good question, actually. And the answer is that it does not matter, because a probability of being equal to minus 2.65 is 0. If you recall the problem of
sure, but
continuous distribution, but you are totally right. You are absolutely correct. All right.
May I ask a less bright question, probably?
You're welcome.
All right. About these two probabilities that you've calculated there, underlined with purple and green lines, how did you exactly extract them?
Well, first of all, we do know these coefficients. We do know these boundaries. And then look, what CDFs allows you to know is the probability of being less than a threshold. So if I want to be inside two boundaries, I do grab the greatest one and I estimate the probability of being less than the greatest. And then I subtract the probability of being less than the lowest of two boundaries.
Yes, I
And
understand.
that gives me a value of being inside of them.
Yes, I do understand that. I mean, the values of these two, of each of these two probabilities, you've calculated 0.996 and
Oh, that's a very good question. Well, then I opened the normal distribution and I found there those boundaries. So minus 2.65 was here. So I just grabbed it. The only problem was that I was looking for a probability of being less than a positive threshold, but the positive one was not given to me. And that was the reason why I was doing these modifications in order to find the probability of being less than 2.6. Any questions still?
I have a question.
Yeah, you're welcome.
We divided by sigma, but what if we don't know the standard deviation in the general population? What if we have only one sample and we know only standard deviation?
Well, that's a very good question. These kind of scenarios are going to be discussed in the second module. Now, currently, we do know the expectation and the sigma of normal distribution, obviously. If we fail to know the population sigma, then we will apply another transformation. So here I did a Z transformation instead of normal distribution. But if I fail to do that, then we could apply the transformation that is called a T transformation or a student's transformation.
Okay, fair enough. Thank you.
Yeah. All right, that's good.
It's clear.
Yeah, that was good. Now let's try to do, let's do this problem. That is a very good one. All right. So let me give you a minute for you to try to do that. Can you guess what the correct result here is? So basically, what do you know here? So you have some random observation, all right? And there is a random variable that is called to be time. And it has a normal distribution, with mean 7 and the standard deviation equal to 2, then the question is to estimate the probability that time, you need to know the time that splits the 20% of fastest and 80% of slowest. So if you know that time is a random variable with a normal distribution, with mean 7 and the variance equal to 4, then you need to know some threshold. Let's call this time B, for example, that splits 80% of slowest and 20% of fastest. Because of the normal distribution, here is a threshold where 80% of slowest located on the left-hand side and 20% of fastest located on the right-hand side. Well, then I'm going to do as that transformation. So I'm going to subtract the mean and divide by sigma. So here is B minus 7 divided by 2. Then left-hand side, then T minus 7 divided by 2 is replaced by Z. That is a standard normal distribution. And then what you need to do, actually, you need then to open the standard normal distribution table and grab there a threshold that splits 80% of chance. And actually, the way you do that is actually the following. So you look into these values and you should find here 0.8. Once you found there 0.8 is going to identify a value that should be equal to B minus 7. To B minus 7 divided by 2. And this is the way how you evaluate this problem. Any questions so far?
No questions.
Yeah, can you repeat the procedure with the table?
So in order to evaluate these threshold, the only you know is actually the probability that should be split. All of these values, I mean, all the boundaries versus the probability they split are given at the standard normal distribution table. So what you do, you open the standard normal distribution table that was shared at the Telegram channel, for example, and there you should find inside the 80% chance, and the coordinates of this cell is going to define the threshold value that you should pick. So for example, the coordinates where 0.8 is located inside this cell, let me do that as an assumption, is for example 1.5 and 0.07. So then I say that it is equal to 1.57. And from that equation, you find what B stands for. And that's it.
Oh yeah, okay, I get it. Thank you.
You're welcome. All right, so let's do the final problem by today. And the final problem that we are going to solve is going to be, well, I wouldn't like to solve any combinatorial problems because they seems to be pretty obvious. But what I would propose is actually to practice a normal distribution problem again. So let's solve this problem. So let's solve this problem. Here you know that the height of man is normally distributed. And the question is to find a probability of those who is greater than some threshold height limit. Well, we are happy enough to say that proportion and the percentage is actually a similar value. All right, so we have a guess. All right, so let's try to do that. I want to know a probability that randomly picked man is over than 190. But this is totally the same as 1 minus a probability that H is less than 190. Then I do the following. I'm going to normalize this by subtracting the population mean and dividing by sigma. Then what you do, you go to the, oh, that's 15. So then the rest of the steps is actually the following. You evaluate what 15 divided by square root of 62 stands for. You go to the standard normal distribution table. You grab these probability that is actually appears to be about 0.2 and 0.3 probably. And then you do know the percentage of the human that are below the 190 in terms of their height, or 1 minus gives you a proportion of those who is above 190, and that's it. So
and why we
what we
can't
did,
do and why we can do it without transformating for 1 minus p of h?
we cannot do that because the standard normal distribution table provides a CDF of H being less than. It doesn't claim values for probabilities that you are greater than some threshold because of the definition of the CDF. Does that make sense?
Yes, thank you.
You're welcome. All right, so this is it. The lecture is over. I'm going to share now the sample mocks, I mean the past papers, so you could have the access to all of these problems. I do recommend you to practice the free response problems. It might be a very good practice. And if you have any extra question during the next week, do not hesitate to text me. All of the extra data and instructions are going to be shared at the Telegram channel.
Well, may I ask you about Bernoulli distribution?
Yeah, if it could be, yeah, you're welcome.
Could you just quickly repeat the idea, because I totally forgot what it is and how to use it?
Well, a Bernoulli distribution stands for a simplified case of a binomial one, when you have only one trial, and that's it. So actually, we never apply Bernoulli distribution for any problem because it's a simplified case of the binomial distribution.
So just another one case when we use Bernoulli's name, but we don't apply it, right?
Absolutely,
Okay,
absolutely.
Can you like send us the slides like today?
Yeah, I'll do that. I'll do that in an hour in the house.
Yeah, thank you. That would be nice.
So sorry, I have another question, one more question.
Yeah, please.
About central limit theorem. There is a quick number 30, and why is it 30?
We will discuss this at the next module. This is not a part of the exam, but we will discuss that. That's a very good question.
And am I right that central limit theorem holds for almost every distribution, even
Yeah,
it's not
absolutely.
normal? Okay.
Yeah, absolutely. All right, guys. So let me wish you to enjoy this weekend, and let's stay tuned for the next week before the exam.
Okay, thank you.